I come too earlier?
I think so, but I have already prepared, so I think we can ask them to join.
That's okay. We'll just wait.
Can you hear me?
Yes.
Okay.
我需要 introduce 这个 discussant 吗？
我觉得要的吧。
就是 do at the very beginning or do at the later?
可能一开始一块儿说。
可以啊，我们可以。
我这现在2个设备在，就是所以回音就是一直在回音。
OK。
主老师。
我们的主角还没到。
我们这个已经在直播了，所以我
们开始了。OK。
Hello， 梁老师。
Hello。So Haipeng, you are now in Harvard University.
Yeah.
Yeah, we're close.
Yeah, I know. But yeah, the current situation doesn't allow me to visit you. Yeah, I would be happy if I got a chance to come and visit.
Yeah, we got to schedule a meeting, a Zoom meeting, after the talk, maybe next few days. We're close, and I've been like 1 year, haven't gone to Boston due to the coronavirus.
Yeah. But actually, I'm not in Boston right now. I still live around New Hampshire.
Oh, okay.
Yeah.
Okay.
But it's still close, just 2 hours drive.
Right. So, Professor Zhu, you are already back to US, right?
Yes.
Oh, I didn't know.
Yeah. When I talk to Professor Zhu, I always confused. Is he still in China or are back to US?
Oh, I was wondering. He was sending messages to me at like 3 p.m. I thought he was waking up like 4 in China.
Okay, I think we can start.
Okay.
And it's my great pleasure to introduce the two speakers. But I think the first one is the Dr. Professor Yanhua Li. And we also have a discussant and Haipeng Chen. And I first introduced Professor Yanhua Li. Professor Yanhua Li received 2 PhD degrees. It's amazing. In computer science from University of Minnesota at Twin Cities in 2013. And in the electronical engineering from Beijing University Post and the telecommunications, Beijing in China in 2009. And he joined the Department of Computer Science at the WPI as an assistant professor since the fall 2015. His research interests artificial intelligence and data science with application in smart cities in many contexts, including spatial temporal data analytics, urban planning, and optimization. Recently, Dr. Li focused on developing data-driven approaches to inversely learn and influence the decision-making strategies of the urban travelers who take the public transports, taxis, sharing bikes, etc. Also, Dr. Li is a recipient of NCF Career Award and the CI 2 awards. And this is about Professor Li. Also, I want to introduce the Dr. Chen. Haipeng Chen is a postdoc in the department in the computer science department at the Harvard University. Before that, he did his first postdoc in the computer science department at the Dartmouth College and obtained his PhD from the Nanyang Technological University in Singapore in 2018. His research lies in the general areas of artificial intelligence, including machine learning, data mining, and algorithmic game theory, as well as their application towards the social good. And he was a winner for the 2017 Michael Mello Collaborative AI Challenge and the running up for the Innovative Demonstration Awards of the IGCAI 19. He has published multiple papers in top conferences. He's some of the program members for top AI conferences and is co-organized for ICL ARL 2021, the workshop from synthetic data generation. Welcome. I think Yanhua, it's your turn now. Yanhua.
Okay, thank you. Thank you, Professor Zhu, for the introduction and inviting me for this opportunity to give a talk on my research. So I'm going to share my slides with the audience. Can you guys see my slides?
Yes.
Okay, great. So, okay, let's get started. All right. So today I'm gonna give a talk entitled "Decision Analysis from Human Generated Spatial Temporal Data." One interesting area that I have been working on for a couple of years. And myself, so as Professor Zhu introduced, I'm an assistant professor in computer science and data science in Worcester Polytechnic Institute. And so let's get started. So before looking into the details of this today's talk, this specific area of analyzing spatial temporal human generated data. So I want to give a brief overview of my research. Okay, so my research covers 3 interdisciplinary areas, including data science, especially the spatial temporal data science, where I analyze a large amount of data from urban area, analyzing their spatial temporal patterns. And another area I'm looking into is artificial intelligence, basically in inverse reinforcement learning and meta learning, etc. And with these 2 upper layer theoretical aspect, so I also work on applications in smart cities, making the urban area smarter. Okay, so with these 3 interdisciplinary areas, so here are some sample topics that are covered in my research. In the first area, in spatial temporal data science, I've been working on human decision analysis. Basically, this is the focus of today's talk, where we analyze human-generated spatial temporal data and to inversely learn their decision-making strategies from the data. And also, we have been looking at the mobility signature identification. So basically using the human beings' data from urban area to uniquely identify them, okay? And also, we use meta-learning to estimate the traffic dynamics, okay? And the second area in artificial intelligence, I've been working on learning F divergence in inverse reinforcement learning or imitation learning. And recently, I also work on continuous meta-learning and reduced rank regression, so on and so forth. And so in the application area, so I work on this commuting with autonomous vehicles, okay? And also in illegal parking detection using shared back trajectories, and also of urban bike planning, okay, using shared back trajectories. Okay, so these are some sample topics my group have been working on. And so today, in today's talk, due to the limited time, I'm gonna focus on the human decision analysis, okay? A few works in this particular topic. All right, so so I'd like to introduce my my team. So without them, so I can't achieve those interesting results. So I have 6 PhD students working with me. So here are their pictures, and so that's it. And okay, so let's get started for the human decision analysis using artificial intelligence. So in this direction, I'm interested in looking at and analyze how people, human agents, make their decisions. Okay, so the human decisions is a broad, covers broad range of topics. Okay, we as human beings, we make all kinds of decisions. Okay, including, just to give a few examples, including, for example, given many books, so which books we want to read, and also when a kid goes into the college, which major to choose. Okay, those are all decisions or choices. And also when we had a baby, how to choose the name for the kid. Okay, and when we had to travel to some city, which hotel to choose. Okay, those are just a sample of decision examples. But here is a diverse range of decisions. Okay, human being usually make. But in my research, I'm only interested in a subset of decisions made by human beings. So those are specifically so-called spatial temporal decisions by human agents. So here are a few examples about what I mean by spatial temporal decisions, including the passenger seeking trajectory from the like Uber or Lyft drivers. Okay, think of the Uber or Lyft drivers when they look for passengers in the urban area. They drop off a passenger. Their next decision when the car is idle is which direction they want to go to find the next passenger. So you can think of the taxi drivers or Uber Lyft drivers. Along the whole day, they are basically making sequence of decisions of where to go to find the next passengers. Okay. Similarly, so in terms of the food delivery service, like Postmate and Uber Eat, those workers take also a sequence of decisions of which next order to take and which order to drop off. Okay, in the next time step. And also another example is the bag sharing system, where in the bag sharing system, those especially the dockless bags in the service, they in many cases they get broken, and the bag sharing company need to arrange the service to recycle and take those broken bag back and fix them. Okay, this is also making sequence of decisions of where to go next to pick up, the next broken bag. And moreover, for the passengers in urban area, they also need to make a sequence of decisions from their home to their working place. Say which transportation mode and routes to take. Okay, from the home to their working place. So these are a few examples of spatial temporal decisions made by human beings. Okay, there are certainly more examples of what I mean by spatial temporal decision. Okay, so in this talk, I'm going to particularly look at, given the large range of spatial temporal data with decisions made by human beings, those information embedded in the collected data, how we inversely learn the decision-making strategies from the human beings. Okay, so learning their decision-making strategy has many real-world applications, and so first of all, we call all those data collected with decisions from human being in the urban area as a human-generated spatial temporal data, in short, HSTD. And as I mentioned briefly, the goal is to learn the human being's decision-making strategy from the human-generated spatial temporal data to learn their decision-making strategy. Okay, and what I'm going to introduce in this talk, the methodology I'm going to introduce is so-called spatial temporal imitation learning. So spatial temporal imitation learning serves the purpose of inversely learn the decision-making strategy from the human agent. And so after learning the human agent's decision-making strategy, those information has many downstream applications. Basically, using the learned decision-making strategy, we can do many things, okay, to make the urban area smarter, make the cities smarter. For example, with the decision-making strategy, we can first of all to better train the taxi drivers, for example, to make them better make decision to find the next passenger. And also with the passengers decision-making strategy can help us to better plan the transit routes for the transportation system planning in urban area. And then last but not the least, okay, so also using the decision-making strategy can help us to train the self-driving cars, okay, so that the self-driving car can mimic how human drivers drive the car, okay, take passengers, choose the routes, so on and so forth. And besides these, there are also more applications with the learned decision-making strategy. Okay, I'm not going to name all of them. Okay, so with these basically this good applications, the goal of this talk is to introduce how to do the imitation learning, how to inversely learn the decision-making strategy. Okay, so first of all, to learn those decision-making strategy, there are a few key challenges. Okay, first of all is the diversity of the human decision-making strategy. All right, that means each individual human agent may have its own decision-making strategy, differing from any other human agent. Okay, so looking at this picture, this is a picture showing the distribution of the hourly earning of taxi drivers. And this data was collected from China in Shenzhen, about 19,000 taxi drivers. We can see the x-axis is the hourly earnings, okay, from very low hourly earning to high hourly earning, okay, across different taxi drivers. And so this means, okay, the taxi drivers are with different expertise. Some of them, less experienced taxi drivers, they only, earn very less hourly earning, versus those expert taxi drivers, they earn much more, in an hour. So this primarily because all those taxi drivers, even though they have roughly the same goal, but their experience and decision-making strategies are diverse and totally different, driving them to have different hourly earnings. Okay, so this is the first challenge of learning the decision-making strategy from human agent. And second challenge, as shown in this picture, is basically trying to illustrate the decision-making factors, okay, are diverse and complex. That means each human agent, when making the decision, they are considering a diverse range of factors and features. So, for example, in the urban area, when the transportation this authority, they try to plan the bus route and subway routes. Okay, they try to develop the bus and subway routes in a way that they can serve the passenger, basically to meet their needs. All right, but in reality, so from the data we collected in Shenzhen in 2014, there were many new bus routes developed. And here is a figure showing 3 of them, okay, 3 representative ones. And the three new bus routes in 2014 are the M44.1, 44.4, and 44.6. Okay, 3 bus routes. And the x-axis is the time in a day in different hours from the morning to the end of the day. And so we can see the hourly, basically the number of passengers on board in each bus route. And the red line, the straight red line, is the capacity, okay, of the bus, okay, and it's around 26 passengers in a bus. But we can see for all 3 bus routes, they have the basically the morning rush hour and the afternoon rush hour clearly. But these 3 different bus routes, the green one, as one of the new bus route, only attract a very small number of passengers over the day. Okay, that means even this is a new bus route, but not many passengers would like to take this bus route. But the other 2 bus routes, the purple one and the blue one, we can clearly see in the rush hour, especially the morning rush hour, there could be more passengers than the capacity take the bus route. So this picture shows that the current transportation planning strategy is not efficient enough to consider the diverse, basically, factors of passenger making their decision to choose the bus routes. So that's why the blue color, this new bus route does not attract many passengers. Okay, so and on the other hand, in US, similar examples, the ridership on new light rail lines at Denver, West, and Norfolk was half that expected for the opening year. So they had the same problem, failed to estimate how many passengers would like to take this route. Okay, so this is another challenge of learning the decision-making strategy of human agent, either in passenger side or at the driver side. Okay, so given these challenges, okay, in this work, we're gonna introduce our work of both analyzing, basically modeling how human agents make their decision, okay, in urban area, and also given this decision-making model, and we'll also introduce the imitation learning strategy of inversely learn the decision-making strategy, okay? And so I'm in the next few slides, I'm going to introduce, first of all, the model, okay, for characterizing the decision-making process of a human agent. And secondly, is the imitation learning. And one thing to note here is that imitation learning has been studied in the literature, even not particularly for spatial temporal data, but has been studied in the literature and has been named differently. So it's called imitation learning, inverse reinforcement learning, and also apprenticeship learning. They are exchangeably used, okay, in artificial intelligence area, okay? So, great. By the way, if you have any question during the talk, feel free to ask your question. All right, so first of all, modeling the urban human agent decision-making process, okay? We think of, okay, the passengers of public transportation are making sequence of decisions, taxi drivers are making sequence of decisions. So here, let's use taxi driver as an example to illustrate how, this decision-making sequence is modeled, okay? So we actually use the Markov decision process to model the decision-making process in urban area. Let's think of a taxi driver, where, so this picture shows a urban area with the road network, and we partition the city or the urban area into grid cells, okay, like those boxes in this picture. And you can think of the taxi driver when the car is idle, okay, it's making a sequence of decisions of where to go, which direction to go next. So we can think of initially the taxi driver is at the grid, at at the grid cell S0, and the driver can make one of 8 decisions of the 8 directions to go, or stay at the current grid cell. And the agent can choose the A0 as moving to the right, okay, as the first action. And then the state transits to the next state, say S1. And similarly, at S1, the agent chooses the next action out of 8 directions and goes to S2. And at S2, the taxi driver finds a passenger, and the passenger has the destination at S3, and then from S3, it takes a transition, okay, by taking the passenger from S2 directed to S3. Okay, then after dropping off the passenger, it do the same passenger seeking process of making decisions which direction to go. So this illustrates the whole process of a taxi driver making their decisions in a day. When the car is idle, which direction to go next to find the next passenger. Okay, so this is nothing but a Markov decision process with the S represent the state space, and A as the action space, including the discrete actions of which direction to go. And P represent the transition probability matrix, okay? The probability of transitioning from one state to another state. And R is the reward, okay? Reward function, say the taxi driver, okay, when it visits a state and taking an action, given the state action pair, how much reward the taxi driver obtains. And the gamma is the discount factor, is discounting the future reward versus the immediate reward, okay? So, and the gamma is between 0 and 1. So in this example, so you can think of each agent, human agent, as a taxi driver, okay? There are 2 factors, 2 functions embedded in this taxi driver governing how the taxi driver makes its decisions. The first function characterizing the taxi driver's decision-making strategy is the reward function. Okay, that means given the current taxi driver state and the action it chose, okay, how much reward, conceptual reward, okay, the taxi driver gonna receive in his mind. And another part of the decision-making strategy of this taxi driver is policy. Okay, it's a function, say, given the current state, the probability of choosing the next action of A0. Okay, so it's a distribution, conditional distribution. So for each agent, human agent, taxi driver, we use these 2 functions to characterize the decision-making strategy. Okay, and these 2 functions are the 2 functions we want to learn from the trajectory data, the decision-making data we collected from the taxi driver. Okay, so given these 2 functions, some work, prior work, model these 2 functions as linear functions in terms of the features of the state. But in general, in recent works, people have basically started modeling these 2 functions as general nonlinear functions and learned by deep neural network. Okay, in general, again, the goal of learning the decision-making strategy from human agents data is to learn the 2 functions. One is the reward function, the other is the decision-making policy function. And when they are modeled as a general nonlinear function, okay, we have the first deep neural network characterizing the policy function with the input as the human agent's current state S. This could be a high-dimensional state feature vector. And the output is a policy. It's a probabilistic distribution for choosing different actions at this particular state. And another function we are going to learn from the collected data is the reward function. Okay, it takes the current state and action, the state action pair as input, and output a reward value characterizing how much reward the human agent is going to collect by taking this state action pair. Okay, so these are the two nonlinear functions we are going to learn from the data collected from the human agent. Okay, and so there has been some literature work studying this problem. Let's start from some literature work before moving on to our approach. So one literature work is so-called maximum entropy inverse reinforcement learning, published in AAAI 2008. And so in this model, we can think of, okay, given a expert agent, like a taxi driver, is using its own strategy, the decision-making policy, to choose where to go in each state. And the policy is usually stochastic. It's stochastic. That means by chances, the trajectory collected, okay, might be different. Okay, think of, okay, using the human agent's decision-making strategy, the policy function, the entire space of these trajectories we can collect from the human agent can range from the zeta 1 to zeta n. Let's say these are these are some samples from the entire population space of the trajectories that the human agent can traverse, okay, when finding their passengers. And each trajectory is characterized as a sequence of state action pairs, okay, from the starting state, starting action, to the terminal state and the terminal action. Each zeta as a trajectory is a sequence of state action pairs, okay? And so the goal of finding the reward and policy function, in fact, is nothing but this equation, okay? The first constraint here. Let's forget about the objective function first. Let's look at the constraint for constraint number 1. And so the goal actually is to match the expected total reward of a trajectory with the average reward of the trajectories collected from the human agent. So on the right-hand side of this constraint, okay, say we collected n trajectories from the taxi driver, and each trajectory, the taxi driver collected our zeta I amount of reward. And the average among all the collected trajectory for their reward is the average total reward of each trajectory. And on the left-hand side is on the population space. We want to find the reward function R and the distribution of all trajectories, the expectation of the reward, okay, match the average trajectory-wise reward from the collected data. Okay, this equation, the constraint, actually is nothing but the goal we want to meet to find the decision-making strategy in terms of R and the P. Okay, but think of, in reality, we only sample a subset of trajectories from the huge space. And if we just meet this constraint, there will be infinite many of solutions matching this equality constraint. Okay, so in the literature, there has been many works, with different ways of breaking the tie. Okay, say matching this expected reward constraint, there are infinite many of solutions. Okay, for the decision-making strategy, but to break the tie, to find one of the infinite many, okay, in the maxent in the maximum entropy inverse reinforcement learning, they try to use this maximum entropy to break the tie. Okay, maximum entropy breaking the tie means that in the objective function. Okay, among all the decision-making strategies in reward and the policy, okay, they want to find the one reward function and the policy function such that the entropy of the trajectory distribution is maximized. So the intuition of doing this entropy maximization is that we want to find the solution decision-making strategy in reward function and policy that hold for this constraint number one. Okay, the expected reward meets the data collected. On the other hand, okay, the maximum entropy means that we don't want to make any further commitment for other unknown constraints. Okay, the only commitment we make is to let the learned decision-making strategy match the expected reward from the collected data, but no other things to commit. Okay, this basically is the maximum entropy objective function to break the tie. Okay, and the constraint number two is a trivial constraint, is making the trajectory population space form a complete basically distribution. The total probability of generating all possible trajectories is equal to 100%. Okay, so and this is the intuition of the so-called maximum entropy inverse reinforcement learning. But one thing you may notice here is that the decision-making strategy include two parts. One is the reward function R. Okay, the other one here is characterized as the trajectory distribution rather than the policy function. Okay, so the policy function is given the current state, the probability of choosing the next action, and the trajectory distribution here is the probability of observing each particular trajectory. So there is a gap. Okay, so to learn the policy, we rewrite this optimization problem, maximum entropy inverse reinforcement learning problem, into the formulation on the right. We did nothing but expanding the trajectory distribution into the form with the policy function, pi of action given the current state S. Okay, so I'm not going to explain the details how this is done, is rewritten, but actually if you do a little bit kind of this mathematical derivation, it's easy and trivial to transform the formulation from the left to the right. They do the same thing, but only difference is they replace the trajectory distribution with the policy of action given the current state. Okay, and the first constraint is rewritten as the expectation of the reward using the learned reward function and the learned policy function. Okay, which match the empirical data. Okay, the average total reward received from this collected data. Okay, so now we have this formulation where we want to learn the reward and policy function to meet the collected data. Okay, and to rewrite this one a little bit, to move the constraint number one to the objective function using the Lagrangian multiplier. Okay, so since this is the equality constraint, okay, we could just move this equality constraint to the objective function by introducing a Lagrangian multiplier lambda without any problem. But we're moving this one to the objective function. We want to make this one as an inequality. Okay, because in reality, in the learning process, to have the learned reward and policy function that the expected reward is equal to exactly the empirical value is very hard. In many cases, given the real data, this optimization problem may not be solvable. It's not a feasible problem. There's no feasible solution. So to mitigate that problem, so in reality, when we move this constraint to the objective function, we make this constraint as a inequality constraint. We wanted the learned reward and the policy function with the expected reward to be as close to the average reward from the data as possible. Okay, that's why we have the multiplier here, and we add a minimum this operator here. Okay, it's not just the equality constraint; it becomes a minimax problem. Okay, so given this process, we have transformed the decision-making strategy learning problem or the reward function and policy function learning problem into a minimax problem. Okay, and given this minimax problem, the formulation, well, this is quite similar intuitively, okay, to the adversarial training, okay, generative adversarial training problem. And here is the connection. Okay, how we could use the adversarial training to solve this imitation learning problem. Okay, just a quick overview of the generative adversarial networks. Well, so in many cases, we want to train a generator given a set of image data or sentence data. We want to train a generator such that the generator can take random low-dimensional input represented as Z and output a like real image, okay, from the collected data set. And so it's in general, we use the two deep neural networks. One is the generator we want and the discriminator, okay, and to solve a minimax problem, okay, as above, is trying to train the generator such that when the so the image generated from the generator, okay, would lead to high reward value from the discriminator, and the real images, the real data after going through the discriminator is also going to give a high value, okay, and the discriminator also trying to minimize or lower down the value when evaluating a generated or fake image. Okay, that's how the generative adversarial network can be modeled as a minimax problem. Okay, in the training process to solve this problem in image generation, it trained the generator, okay, so that the random code Z going through the generator get a generated image, and the generator trying to generate image that will get a higher output from the discriminator, but discriminator will try to lower down the value of a fake image. They are basically trained jointly. And the same thing, so this generation process, the generator can also be trained to generate human sentences. Okay, so this is the idea, brief idea of the generative adversarial network. And when we look at this formulation of the GAN model, is well, quite similar to the imitation learning formulation we just derived in this slide. Okay, so in fact, there is a rigorous mathematical connection that this imitation learning problem can be modeled exactly by the generative adversarial networks. Okay, so with this idea, this imitation learning problem, the minimax problem, can be coupled with the GAN model, and in that way, we are treating the generator in the GAN model as the policy network, and the discriminator in the GAN model as the reward function, Okay, and in this case, the policy network takes the state as input. The state could be, if for taxi driver, the state could be the surrounding area, all kinds of features in different channels. For example, the traffic speed, volume, and so on and so forth, and even weather, okay, representing the nearby region of a particular location, okay, representing the state of the taxi driver, okay. And the policy gonna output a probability distribution representing the distribution of choosing different actions, choosing different directions to go, to look for the next passenger, okay? So this policy as a distribution is usually a stochastic function, okay? And after getting this stochastic function of the taxi driver choosing different directions to go, and we're gonna sample with from this distribution to sample a action A from the distribution, and then the original state and the sampled action together as a state action pair will be evaluated by the reward function. Okay, the reward function, okay, if output a high value close to 1, that means this state action pair is more likely to be the real taxi driver, okay, rather than the generative. Okay, so this is quite similar to the GAN model, and it's the way how we solve the imitation learning problem using the GAN model. Okay, and well, so in reality, when we think of, we collect a large amount of taxi driver or Uber or Lyft driver trajectories in urban area. Okay, using this idea, using the GAN model, we could potentially learn the decision-making strategy in terms of reward function and policy function of the taxi driver. But in reality, there are many real challenges, that's so-called spatial temporal challenges. One of those challenges is so-called sparsity challenge. Okay, so using an example, say given one taxi driver, when the taxi driver take passengers, look for passengers in an urban area, and it may traverse a big range of the urban area when finding passengers. And if we use the this GAN model to solve this problem, that means across the whole city, okay, the taxi driver is going to use a unique strategy in terms of reward function and policy function when making decisions. But this is not the case, okay? This is not the case. That means the taxi driver, when at one side of the city, may use a different strategy from when the driver is on the other side of the city. So this is from the real data. We take one taxi driver as example, and the orange color and the purple color are the areas covered by the data collected from this taxi driver. And also this taxi driver's home is in this red dot area. It's, her home is over here. And so we split this urban area into two halves. We call them west area and the east area. Okay, and after getting the two set of data from, for the same taxi driver, okay, we try to extract the decision-making strategy from, the west versus the eastern area, and we compare the decision-making strategy from, learned from the two areas, okay, and they are different, okay. So we illustrate this by this table. Okay, we solve this problem not basically using the maximum entropy inverse reinforcement learning, and there are two features we use as example. one feature that the taxi driver is considering when making decision is the time, the current time from the starting time of the day. Okay, and so usually every taxi driver has a starting time, right? And the time, the feature time from start is the current time from the starting time. And the traffic speed is a given area, whether the taxi driver prefer to go to an area with high traffic speed or low traffic speed to look for the next passenger. Okay, so I mean this entries in the table, okay, means the weight, how much the taxi driver consider this feature. Okay, it's a positive value means the taxi driver will prefer the positive and high value for this feature. Otherwise, if it's negative, that means it's going to prefer the low value for this feature. Okay, so let's try to look at the first feature. That's the time from start. On the east, that means when the taxi driver is on the eastern side of the city, it has a positive this weight to this feature. That means it prefers high time from start, okay, to find a passenger in the eastern area. High time from start means at the end, almost close to the end of today's work, the taxi driver will prefer to work on the eastern side. And on the west side, okay, it's negative. That means the taxi driver prefer lower value of the time from start. That means the taxi driver prefer to work on the west side when it's the early time in a day of work. Okay, so this is totally opposite. Okay, on the other hand, for the traffic speed, okay, on the eastern side, the taxi driver prefers areas to go to find the next passenger with as high traffic speed as possible. And on the west area, the taxi driver makes totally opposite decision, would prefer the areas with as low travel speed as possible. Okay, this can be explained as follows. The east area is primarily the downtown area. Okay, this is in Shenzhen city in China, and the eastern area is the downtown area. Okay, it's usually with high traffic volume, and in many cases there are congestion, etc. And the taxi driver would prefer higher speed area, okay, to avoid the traffic congestion. Okay, and on the left, the west side is rural area in Shenzhen, and taxi drivers, because there are many highways, you can see there are many highways. The highways are with a high travel speed, but taxi drivers wouldn't choose the highways to find a passenger. That's why on the west area, taxi drivers would prefer the areas to look for passenger with as low travel speed as possible. Okay, so this example illustrates that given the trajectory data collected from taxi driver across different areas in the urban area, they may adapt different decision-making strategies to look for the next passenger. Okay, so this motivates us to learn the decision-making strategy with more targeted area and also targeted taxi driver. Okay, the goal is that we want to share knowledge, okay, across different drivers and across different locations. Okay, and so you may notice here, the one taxi driver, the data collected may only cover some area, not the entire urban area. Okay, because the driver has its own preference, and usually it only covers part of the city. And the gray color are the areas the taxi driver would usually not go to. Okay, so in this case, we want to also learn the decision-making strategy across drivers by sharing knowledge across drivers. Okay, how we do that is that beyond what we have done have introduced. So basically, this GAN-based model with the policy network and the reward network, learning the policy and reward for an individual taxi driver or an agent. Okay, we want to characterize, okay, their factor of location and taxi driver by introduce a condition, okay, besides the state of the taxi driver. The condition include both the driver ID and also the location, the region ID, okay, as input into the policy network. And also the same condition after going through the policy network, getting the policy and the action sampled, okay, the state action, the state and the generated action will together with the same condition as input into the reward function. So the reward function not only judge and evaluate how good, how real this state action pair is, but also try to check whether the state action pair match the condition or not, to match the condition or not. Okay, so this is basically we use the conditional, so-called conditional generative adversarial imitation learning to solve this problem. Okay, the goal is to learning a target this taxi driver's policy from behaviors in similar region and from similar drivers' trajectory. Okay, and so this is the approach we proposed, and we evaluated using taxi trajectory data. And we use data from 2016, July to September. And we choose those experienced drivers to do the validation. Okay, those taxi drivers with high hourly earnings. Okay, and so due to the limited time, I'm going to skip the description of the features we used, and we compared our approach with the baseline approaches to measure two metrics. One is the L2 norm, the other is KL divergence, to measuring the difference from the ground truth policy distribution versus the learned policy distribution. Okay, and so these are the baselines we compared with the linear model of maximum ARL and the maximum causal entropy ARL and the relative entropy ARL, and also compared with the basic Gale model generative adversarial imitation learning, and with our proposed approach of conditional Gale. Okay, so when we compare with the baselines, our approach always get the lowest divergence from the ground truth policy distribution. The red one is our approach, always have lower divergence in KL divergence and L2 norm comparing to the baseline approaches. Okay, so this is the work I spent most of the time to introduce about how we develop imitation learning to learn human decision strategy. And we also studied other challenges, say when the passengers choose their transportation modes and routes from the home to the working place. We model it as a multi-agent imitation learning, and we got a paper in WWW, the web conference. And also another challenge and problem we solved is so-called trajectory Gale. We go beyond the Markov decision process, which assume there's only one step this dependency. In reality, the taxi decision-making strategy is basically no longer this Markov decision process. It has long-term dependency across space and temporal. And this is another work. If you are interested in, you can look into this works. I'm not going to introduce in more details. All right, so for some future work and including works we are working on the given the decision-making learning strategy, okay, how we use those knowledge to basically design incentives to drive the decision makers to follow certain policy that the government or the transportation authority expected. Okay, for example, to cover the rural area, to motivate the taxi driver to go to some rural area. Okay, and also when design this incentive mechanism, how to consider fairness, okay, across the passengers and also the drivers. Okay, that's one direction. And another one is the basically meta learning human decision strategy. We can think of there are many taxi drivers, human decision makers, and we can think of so given a new agent, how we can adapt the knowledge learned from other decision makers to quickly adapt the diversity of human agent. Okay, and also another direction is given this human decision making strategy learning process, how we can enable it as an online learning process. Okay, we have the trajectory data coming in as a stream. Okay, how we design this decision making strategy learning process as an online learning. Okay, so these are the ongoing and future works we are doing. And all right, so here is the summary. And today I spent some time talking about one aspect of my research on decision analysis from human-generated spatial temporal data. And the foundation is using the GAN model to solve it, but with different variations to solve different challenges in urban area. And also this general approach has many applications in real world of training taxi driver, starting the food delivery service, passenger decision making, so on and so forth. All right, and here are the references cited in the slide. And that's the end of my talk. Thank you, and I'm happy to take some questions.
I think Hepon, is your turn.
Yeah. First of all, thank you so much, Dr. Li, for the great talk. It's really insightful. Especially, I'm very enjoyed your explanation about the relation between the max entropy inverse ARL and the generative adversarial nets. Yeah, I have a few questions.
Yeah.
So first of all, so you were talking about using the inferred policies from the drivers to help like design the mechanisms to incentivize the drivers to behavior like the way that the government wants or the public wants. So have you also thought about like interpretability of the policies or their actions? What, for example, what factors are playing an important role in driving their decisions?
Yeah, that's a good question. So it's about the explainability of the learned policy network and the real world network. So this is another challenge actually our group have solved and published in KDD 2020. It's explainable, we call it X scale. We actually, we use the explainable AI, develop an explainable AI approach to couple with the Gale approach that we can learn not only the local explanation and also global explanation of the learned deep neural networks. Okay, so in more details, probably today due to the time limit, I'm not going to explain in more detail, but in the paper in 2020, we have a paper in KDD explaining that.
I'll be happy to read it in more detail.
Yeah.
And another question is, it's just not sure if have you, because in the motivation example that you showed, one of the reasons that you use the conditional Gale is the sparsity of data you have.
Yeah.
So have you considered maybe cluster the different drivers first, and then say treat them as a single entity and learn learn a policy within this cluster, so that in this case you have more data to train.
Yeah, that's a good point. Actually, we consider that when we work on this problem. And first of all, no matter what approach we come up with or use to do the clustering of the drivers based on some sort of similarity, this is nothing but a heuristic. We need to come up with the good reasoning of why this clustering makes sense. But in fact, in this conditional GAIL, we don't necessarily need a clustering, because we just treat each individual taxi driver as an individual cluster, quote-unquote cluster. And even though we have, say, thousands of taxi drivers, okay, with the conditional GAIL model, since we are treating each taxi driver, okay, as a condition, this conditional GAIL would learn the quote-unquote the distribution across different taxi drivers. Okay, similar to conditional GAN, it assume, I mean, even taxi driver is, you can think of taxi driver, the identity can be viewed as a high dimensional distribution, but with sufficient number of taxi drivers, the conditional GAIL can for sure learn the distribution across taxi drivers. That means if you have another, say, new taxi driver coming in, the model would be able to use the similarity of the new driver with the the training driver to mimic its policy.
I see. Yeah, that makes a lot of sense. So, so if you use a condition as a kind of feature,
yeah,
you don't have for a new driver, you can still use a derived condition for that driver and just feed that into the learned model.
Right.
Yeah, I'm not sure if I still have enough time, but already 9. But let me ask the last question.
Yeah, so, after that we can take it offline. We don't want too much time for the audience.
Yeah, definitely. So my last question is, since you're working a lot on spatial temporal data, I'm not an expert in this area, but what do you think are the general properties in these types of problems, and have you considered like extending your the methods that you propose in this and the series of papers that you do to other domains?
Yeah. So basically, you ask 2 questions. One is the spatial temporal data, the unique challenges associated with the spatial temporal data. In general, yes, for sure. So from many years of study, the general and usually the key challenges with spatial temporal data are the spatial and the temporal dependency in the data. Spatial dependency means that, like I used in the taxi driver data example, across the road network, there are definitely spatial dependency. For example, the traffic speed, traffic volume, they have a strong dependency across the road network. The nearby regions would likely have similar this driving speed and volume, etc. This is one challenge needed to be characterized in studying this type of data. And another challenge is for sure the temporal dependency. Okay, that's in work I briefly introduced is this variable length decision dependency, because when the taxi driver making decisions, they are not just following exactly Markov decision process. The decisions made along the time horizon would have high temporal dependency. Okay, so this is another challenge usually present in the spatial temporal data. And in terms of the question of what other areas that this approaches I proposed can be potentially be generalized to. So that's good question. So far, I mainly focus on the urban area data, but I think There are also other areas, like recently we also studied the mobility prediction of human being given COVID-19 in US. So there are many other things like human mobility, etc. Can be studied using some approaches we have developed. Yes.
Thank you. I personally was recently working on a project related to wildlife preservation, and there we want to somehow understand the behavior of the poachers, and maybe I think there's some similarity between the transportation data and the poachers' behavior data, because I can imagine it also be in spatial temporal data.
Yeah, interesting. I'm happy to talk to you more offline. Yeah.
Sure. Yeah. I wouldn't keep the audience to waiting for so long. So just.
Is there any question from the audience? If you want to ask a question, you can type. It seems we don't have more questions. And thank you guys for having these wonderful talks. We can chat afterwards.
Yeah.
Thank you.
Yeah, thank you all. Have a good night.
Have a good night.